Welcome back to ECE 442-542. We're still in lecture 5.2, which is dealing with performance specifications and the corresponding z-plane pole locations in a second order system. Remember, we have the three different shapes. We have circles for settling time, hearts for percent overshoot, and wedges for peak time. This particular segment, we're going to focus on the hearts, or the logarithmic spirals, which correspond to percent overshoot in terms of a design specification. If somebody now gives you a percent overshoot, they say, oh, I can tolerate a 30% overshoot. You can now, using this equation, solve for zeta. And this equation is solvable or determined from a second order underdamped system, and we know how to compute percent overshoot if somebody gives us data points. In the S-plane, here again we have two different complex planes. We have the S-plane. This picture or this particular screen may look a little busy. Let's just try to think our way through it. In the S-plane, we are really focusing now on a particular pole location, and let's say that pole location is now at minus zeta omega sub n plus j omega sub n square root of 1 minus zeta squared. The real part of that pole is now at minus zeta omega sub n, which is this distance. The imaginary component of that pole is now this distance, which is omega sub d, or that's omega sub n square root of 1 minus zeta squared, where omega sub n is the hypotenuse of that right triangle formed by the real component and the imaginary component. That's this location in the complex S-plane. The other aspect of this picture that I want you to get comfortable with is the fact that we're going from no damping at zeta equal to 0 all the way down to real pole damping or no oscillation. We're going from sustained oscillation, zeta equal to 0, to no oscillation at zeta equal to 1. And if we went on that same radial distance away from the origin in the S-plane, our natural frequency would stay the same, omega sub n. If we had a different natural frequency at the same zeta value, zeta again is determined by this angle theta in the complex S-plane. For a fixed zeta value, then we are staying on this particular angular location from the real axis, and if we increase the natural frequency of our system, we would be then looking at a natural frequency, let's say omega sub n sub 1. Then we move further away, our system gets faster, we have an omega sub n sub 2, we get even faster, and we go out to omega sub n sub 3. Where do those points in the S-plane translate into in the complex Z-plane? First, if we were sticking solely on the imaginary axis, we would have, in the S-plane, we would have no damping of our sinusoidal response, and that would then correspond to this zeta equal to 0, or the unit circle curve in the Z-plane. If, however, we start increasing the zeta value on our way towards zeta equal to 1, then what we're trying to do is figure out how do these particular constant value of zeta translate into shapes in the Z-plane. If we fixed, let's say that we now are fixed at this illustrating angle right now in the S-plane, which is this blue line, that might be a zeta value of maybe 0.6, corresponding to a zeta of 0.6. What does that look like here in the z-plane? Well, we can find that by looking at this S value parameterized in terms of zeta and omega sub n in its z-plane translation, where z is equal to, remember, z is equal to e to the st. That relationship we know. And the other thing that you may try to keep straight is we have thetas in the S-plane. We have a theta sub d in the z-plane. Theta sub d is measured with respect to the positive real axis in the z-plane. Theta is measured with respect to the negative real axis in the S-plane. R in the z-plane is the distance we are away from the origin. What we want to do now is see how does R, capital R, and theta sub d, how does that change, because that will change the location in the z-plane. How does that change if we fix zeta and vary the natural frequency omega sub n? What would that look like if we just looked at 3 different natural frequencies in the S-plane? What would that look like in terms of a shape in the z-plane? Here I'm simply recalling the relationship between zeta and theta, where theta is in the S-plane, in this picture. We know that if we wanted the cosine of theta, that would now be adjacent over hypotenuse. That's zeta omega sub n over the natural frequency, or that's zeta. We now have this direct connection between the damping ratio zeta and the angle theta. And if we had zeta, we could solve for theta. If we had theta, we could solve for zeta. That's in the S-plane. If we now map that through what we know the relationship is between z and s, z is equal to e to the st, and s now we've parameterized in terms of the damping ratio zeta, which appears here, and the natural frequency omega sub n, which appears in the real part of s and the imaginary component of s. Let's now split that exponent into 2 exponents. Using this property of exponents, we now have a property of this first piece, e to the minus zeta omega sub nt. We're distributing the sample period through both terms in the upper equation, and then we're simply pulling out the 2 different pieces, or realizing that some number, let's say x to the a plus b, is the same as x to the a times x to the b, where a in this case is minus zeta omega sub nt, x is actually e, and b is j omega sub nt square root of 1 minus zeta squared. Well, if you look at this particular factor is just an angle, theta sub d, and the preceding exponential just represents the magnitude of z. So we now have r e to the j theta sub d, and sometimes you might see that written in a more compact phasor form, where we might say r at an angle of theta sub d, but that's really just saying that that's r e to the j theta sub d. And you could use Euler's formula to get out the real component and the imaginary component of that z value. What happens now if we fix zeta in this r expression and theta sub d? We see that r occurs in both. And what we are going to do is vary the natural frequency omega sub n along this particular curve and see what that translates into in the z-plane. Here we see that omega sub n is going to be changing the radius and the angle at the same time, maybe in opposite or reciprocally related ways. So let's see what that does. If we look at R, and if we increase omega sub n, R is related to omega sub n, or omega sub n enters into R through this negative exponent, which means if we make omega sub n bigger, R is going to shrink. Conversely, if we look at what happens in the second factor of this factored form of z, e to the j theta sub d, as omega sub n is increased, again, t is fixed and zeta is fixed, so zeta squared is fixed. This factor is now just a constant, and if we increase omega sub n, that increases theta sub d. As we increase omega sub n, what we are seeing then is that we're actually, on the left, we're marching omega, the natural frequency, to higher and higher, so we're increasing omega sub n. The radius as this exponent, omega sub n 1 to omega sub n 2 to omega sub n sub 3, as omega sub n gets bigger, that gives us a e to the minus bigger number, so that's r's are getting smaller. So in fact, as we increase the natural frequency, we're actually decreasing the r's. Conversely, as we increase the omegas in the theta expression, we are actually increasing theta sub d. So hopefully you can see that as we are increasing omega sub n, here is omega sub n 1, here's omega sub n 2, and here's omega sub n 3. But we said that these are getting bigger from right to left. Conversely, here's omega sub n 1, here's omega sub n 2, here's omega sub n 2, n 3, and those are getting bigger as you go from left to right. Which really is saying that in the z-plane, as we, let's say here is r1 theta 1, then we're shrinking r1 down to r2, and we're increasing theta d1 to theta d2. So now we make r smaller and theta sub d bigger. R then at omega sub n3 gets smaller and theta sub d gets bigger. So hopefully you can see that that's why we now can have these logarithmic spirals corresponding to fixed values of damping ratio. So as we now fix zeta, that produces logarithmic spirals in the complex z-plane. And maybe if you just wanted to sort of ask yourself, where, let's say, did zeta equal to 0.7 come from, or what can we think of there? Remember we said that was sort of a Goldilocks value. We can actually convince ourselves of what that corresponds to by drawing some triangles. Let's say this side is 1 and this side is 1. Now we know that if this is a box, and the diagonal of that box is now the hypotenuse of this right triangle, this hypotenuse has the square root of a squared 1 plus b squared 1 squared, or this is now the square root of 2. This angle, theta, is now going to be, if we said, oh, what's the cosine of 45 degrees, which is what this is. This now is splitting. It has an equal real component or opposite component, or adjacent component, and real vertical component or real opposite component. This is now adjacent over hypotenuse. This is now the square root of 2 over 2. Or this is now 0.707. So now if we had an angle theta equal to 45 degrees, that's in the S-plane going to give us this Goldilocks value. So that's where you can sort of keep track of this zeta value of 0.7 or this nice value of 0.7 and where that might be relative to zeta equal to 0. And where is zeta equal to 1? Zeta equal to 1 is on the real line in the z-plane. And going from the unit circle to the real line, as that heart collapses, our zeta values are getting bigger. Going from zeta equal to 0 to zeta equal to 0.1, 0.2, our hearts are getting smaller, and that corresponds to less and less percent overshoot. So these logarithmic spirals are associated with the shape of percent overshoots, giving us hearts.